So now that we've talked about stress, we'll talk about something that's pretty closely associated with stress, and we talk about it in conjunction with stress a lot in this class, is something called strain. And strain describes how a body is going to deform. So it's a description of deformation, a deformation that occurs under stress. So just as we learned about normal stress and shear stress, we also have normal strain and shear strain. And each of those cause these strains. Stress is what causes a strain, and applied stress gives us a strain. So we'll go ahead and look at normal strain first. Just like we had normal stress, we have normal strain. And the way this deformation is represented is if we have some rod that's just sitting here and some force is applied to it, right? So there's some loading on it, some force is applied to it, it deforms, it gets longer, right? Which is kind of intuitive to us in thinking about toys we had as kids, right? Like Play-Doh. If you play with Play-Doh and you have a little Play-Doh snake, you roll out a little Play-Doh snake for yourself, and then you stretch it out, you see it start to get longer. It starts to deform before it eventually gets too thin and breaks. Right? So it's a description of this elongation that this is going through due to this normal stress. So normal strain is an elongation or contraction. It doesn't have to be pulling out. It could be squishing something in. Elongation or contraction of this line segment, right? And we write this using the equation, or we calculate this using the equation epsilon. Epsilon is your normal strain. So this is the normal, that's your normal strain term. Equals, I have this initial length here, right? This is my body before it undergoes the deformation. Then once it's under that normal stress, it deforms and becomes longer. It's a description of that change. So it's the length minus the initial length divided by that initial length, right? So it represents the change in length per the original length. So sometimes you'll see this difference here called delta. So this is a lowercase delta. All right, delta over the initial length. Right, so that delta is just the difference between this initial length and the final length after it undergoes that deformation. Here's our equation. And you'll notice that we have a length term over a length term, right? If we had, say, this was, 1 meter and delta was 0.1 meters, we would have 0.1 over 1. And that would technically give you something that's dimensionless, right? But for our units for normal strain, we typically keep the length units in there. So instead of leaving it dimensionless, we usually keep our units as meters over meters, or inch per inch, because we're describing how it changes per unit length. So if we had something really long, it might have the same strain as something really short, and it would just be the length per length that it's undergoing. So it could be meters per meters, inch per inch. Even mismatched units would be perfectly fine. You could use millimeters per meter, or even micrometers per meter, because typically the deformations are going to be really, really small, right? Like if you try to stretch out a metal rod, you probably aren't going to be able to see it stretch very far, especially if you're just trying to do it with your bare hands, right? But it's happening on a microscopic level, right? So it might be only micrometers that it's moving if you're trying to cause a strain, a normal strain in a metal rod, whereas something like Play-Doh, you can see that strain it might be has a greater value of strain that you can see and measure. But typically, we leave the units there. We leave the length per length units. So let's take a look at an example. So in this example, we have this ring hanging from the ceiling by wires AB and AC. And we want to determine the average normal strains in each of those wires if the ring is moved from A to A prime, right? So it's shifted over from its original position because of that force P by 10 millimeters in the X direction and 20 millimeters in the Y direction. So it's moving 10 to the left and 20 down. So we want to determine these, the average normal strain for each of them. And again, that average normal strain equation is that epsilon is the length. Sometimes you'll see it as length prime minus length over length, and what that's the same as the whatever the new length is, right? So the location of A prime minus the initial length. So these are just kind of some notation differences, but these are the same thing, right? It's whatever the new position is minus old position over old position. So we'll need to find for each wire their initial length and their final length, right? So not too many things to find, just those four lengths is what we need. So my initial lengths, I'll notice that AB and AC each make a 3, 4, 5 triangle, right? This distance here, I have 3. This distance here is 4, giving me this nice 3, 4, 5 triangle. So my initial length for AB is going to be 5 meters, which is the same as my initial length for AC. Easy enough, we have half of the lengths just from that prompt there. So now we'll need to find our other 2 lengths, which we'll have to do a little bit of shifting, right? So our AC gets shifted over. We look at this length AC here. Length A prime, C I should say, A prime to C is moving to the left by 10 millimeters. So this new distance here is going to be 3 meters plus 10 millimeters, right? It's adding on to that length. We had the 3 meters and then plus 0.01 meters. So that gives us 3.01 as our top length. And then our side length here is our 4 meters that gets shifted down by 20 millimeters. So it's adding a 20 millimeters to it. 4 meters plus 20 millimeters, 0.02 is 4.02. And now, of course, we'll have to do Pythagorean theorem to find what this length of A prime C is. So length of L prime, or L A prime C, length of A prime C is going to be the square root of 3.01 squared plus 4.02 squared. If I punch that into my calculator, I get 5.022 meters. And then I would need to do the same thing with B A prime. So here's A prime, here's B. My X distance is now being moved in closer to that 3. So it'll be that 3 meters minus the 10 millimeters, right? It's being moved in this way by 10 millimeters. So this is going to be 2.99 meters. And then my Y direction, it's still being stretched down. So this distance here is again the 4.02. So my length of A prime B is going to be the square root of 2.99 squared plus 4.02 squared. And when I punch that into my calculator, I get 5.01004 meters. So now I have all the ingredients, I just gotta stick them in the pot and cook them. So let's go ahead and plug those into our equation. I'll write my equation down here again. So for my strain of AB, we'll start with, it's going to be that, again, it's the length, it's that new length minus old length, right? So in this case, it's going to be L, length of A prime B minus length of AB over length of AB. And that equals, what was our length? It was 5.01004 minus 5 over 5. And all of those units were in meters. So my strain here, the strain AB is undergoing, is 0.002 meters per meter. Right, easy enough. You could probably figure out this next one on your own, right? The strain of AC. Go ahead and do that, compare to mine. Our 5.022 meters minus 5 all over 5. Punch that into our calculator. We get the strain of wire AC is 0.0044 meters per meter. And again, you don't necessarily have to write it like this. We could have written this as, if I move my decimal point over, 4.4 millimeters per meter. So my strain here is saying that when this force is applied, when this stress is applied, and I undergo this deformation, the deformation is that it moves 4.4 millimeters per meter of length that I have. That's what this is saying. That's what the strain is describing. It describes that deformation.